Okay, so time to get started. And we are actually going to get started with Math 212 material today instead of checkerboards and dominoes. Okay, so the first thing we're going to talk about is vectors. What's a vector? It's going to be a very important, fundamental object of study in this course. So we'll lead into what vectors are by, let me remind you what points are. And we'll start off in R2. This should be extremely familiar. We commonly see this as the XY plane, right? I'm going to use X1 and X2 instead of X and Y. You'll see why in a few minutes. But hopefully this is super old news, right? If you have a point, right, then to that point you can associate a couple of coordinates that you can combine together to make an ordered pair that you can consider to be an element of this set of all possible ordered pairs, right? So in this way, by projection to these axes, for every geometric point, there is an associated algebraic object here that we call an ordered pair. Right? So the plane is the collection of all points. R2 is the collection of all of these ordered pairs. Okay. All right. So super old news, except perhaps for a little bit of notation or terminology or something. Okay. So slightly new, perhaps, is the idea that we can do the same exact thing in space. We don't have to constrain ourselves to what I'm going to call 2 dimensions. So I can look in 3-dimensional space as we think of it, and for every point, right, there is an associated trio of coordinates that I can combine together to make an ordered triple. It's the same idea, right? Okay, and then likewise, I could call this 3 space, or I could call this XYZ space, depending on my choices of coordinates, whatever. And the collection of all ordered triples we'll call R3. And very often I'll use R3 to refer to the space, and the distinction's pretty clear. Okay, all right. Now, it feels like this is as far as we can go. I mean, after all, can we really define R4? I mean, what is R4? Is time the 4th dimension? What about R5? Ooh, creepy, right? Is there a 5th dimension, or are we just talking about science fiction at this point? Right? Well, here's the thing. We can't geometrically visualize what these spaces look like, but notice that's not at all essential in our defining R2 and R3. R2 is a collection of all ordered pairs of real numbers. I didn't say anything about visualizing, right? R3 is a collection of all ordered triples of real numbers. I didn't say anything about visualizing anything. And, well, likewise, I can talk about all ordered intuples of real numbers. That's Rn. Can I visualize Rn? Not really. Okay? But I can still define it, still write it down. Now, a lot of people make the mistake of thinking that, sure, you can write that down, but this is all completely abstract and has nothing to do with, unless you're some sort of pure ivory tower mathematician, this has nothing to do with me, right? Absolutely false. This is extremely important in lots of extremely applicable, very gritty real-world fields. So here's an easy example. Let me remind you that let's talk about economics, right? Nobody thinks of economics as being, abstract or pointless, right? Economics is very real-world, very applicable, very relevant. And you can write down equations that involve economic variables, like price versus quantity, if you've had Econ 101 or whatever I forget what the course number is here. But you can write equations involving those 2 variables, and you can draw those pictures. Right? More to the point, you can write the equations. You can write equations that relate price and quantity. Well, you can also write equations that relate price and quantity and some other economic variable. Right? And likewise, you can write equations that involve more than 3 variables. this isn't at all crazy, right? I mean, maybe you're starting a small business and, okay, well, what price are we going to charge? What quantity are we going to produce? What interest rate is the bank giving us? How much risk are we willing to take on? There's lots of economic variables that are relevant in a business running in an economy, right? So you could really easily talk about a system of equations perhaps that involves 9 variables. Well, you are doing business in R9. You can't visualize it, right? But nevertheless, it remains. You are doing business in R9. Right? So, in Math 212, in this course, most of the stuff that we're going to do, we are going to talk about R2 and R3 because it's nice to be able to visualize things, right? It's comforting and satisfying. There's intuition to be gained there, and that's great. Right? But I want to emphasize most of the formulas that we're going to write down, however usually constrained to R2 and R3 they might be, they are just as true in R9. And if you're doing math in R9, like in econ or engineering or whatever, I mean, there's lots of situations where there's multiple variables running around that are related by way of equations. Right? Keep in mind that you can talk about multivariable techniques in R9 or R23 or whatever the case may happen to be, just as well. Okay. All right. Okay. So let's see here. It looks like we are out of chairs. So I'm sorry.
You're good.
Are you an enrolled student? Mm-hmm. Okay. Is anybody here not an enrolled student? Yeah. You're a waitlist student. So I'm going to, out of fairness to enrolled students, I think I have to ask you to let her have the seat. But you're very welcome to stay.
I can find a seat. I think we should switch here. I'll try to find a chair.
Yeah, if you want to try the room next door, there might be a chair there. So anyway, thank you for being understanding. I appreciate it. Yeah. No, it's understandable. Okay, so now let's talk about vectors. What is a vector? A vector is going to sound like a very different thing, and it is in a lot of ways, a very different thing. So here's our definition that I want to use for a vector. A vector in Rn is a pair. It's a combination of 2 other concepts. A vector is a direction paired with a magnitude. Okay, so we have another. Are you a waitlist student? No? Okay, all right. Are you waitlisted? Okay, yeah. I'm sorry to have to. Yeah, but we gotta play by the rules. Yeah. Okay, so a direction and a magnitude. Now, this does seem like a sort of an odd pairing, right? Why would I pair a direction and a magnitude? What is it? Why do directions and magnitudes relate to each other? It seems weird until you start to realize how many extremely natural things there are, physical examples and geometric examples of things which are very well understood with a combination of a direction and a magnitude. So, for example, this is, I think, the easiest example, a displacement. The idea of a displacement is, look, I was here, now I'm here. What was my displacement? Well, I was here, now I'm here. I moved in a certain direction by a certain distance, and you can interpret that distance as being a magnitude. So a displacement, again, supernatural concept, is a vector. It's a combination of a direction and a magnitude. And then there's lots of other examples. Velocities, if you think about it, a velocity, you're going in a certain direction with a certain speed. You can interpret the speed as being the magnitude. Right? Forces. Common mistake, a common oversimplification that happens in high school physics classes. They describe forces as being scalars. Well, they're not. Forces are vectors. Forces have a direction. If you don't believe me, hold up your pencil and drop it and see if it doesn't always weirdly go in the same direction. Right? The direction is part of what the force is. It's not just a number. Right? So forces are a direction and a magnitude. The magnitude being, well, how much does the thing weigh? Here's a weird one, but the way fluids flow. Let's take, for example, in this room, there's air. Right? The air is not 100% stationary. The air is kind of moving around like a fluid, a little bit. Well, at a particular location, at this spot right here, let's say, there is a vector that describes the fluid flow. The fluid, the air, is moving in a certain direction, probably away from my mouth because I'm talking, right? So there's a velocity of fluid in that direction. And then what magnitude would I associate to the flow of air there? Well, there's different things that you can do. You can talk, and there's a whole, this is going to come up prominently in chapter 15, so I don't want to go off too much. But you could talk about, in that direction, per unit area, how much quantity of air is passing through that area, or something like that. You might choose to just talk about the speed. So literally the velocity of the air at that point. There's different ways that you can do it, and they have their different merits and applications. But anyway, the point is, flows are described by a direction and a magnitude. Okay. All right. So now a common choice is to use an arrow to represent a vector. This is a common choice because, well, after all, an arrow pretty clearly indicates a direction. And then by way of how long I make it, I can let that length represent the magnitude. Right, so arrows are super choices to represent vectors. There's one awkwardness about using arrows to represent vectors. Keep in mind that vectors, again, a direction and a magnitude. They're just direction and magnitude. Vectors, by contrast, they have a direction, they have a magnitude, they also have a location. Right, there it is. Right? I mean, this arrow is physically in a different place than that arrow. So it's just an awkwardness of the choice, right? Using arrows to represent vectors is just not perfect. Arrows, in some sense, say a little too much, right? So just keep in mind when you're using arrows to represent vectors, for example, here I've used 3 different arrows. They're all representing the same vector, because these arrows all point in the same direction. They all have the same magnitude, so they're representing the same vector. Does that make sense? I hope that's a clear distinction. So, got to distinguish between arrows and vectors, and be aware that when you draw an arrow representing a vector, you're making an arbitrary choice of where to draw it, and don't attribute any particular significance to that choice of where you choose to draw it. Okay. All right. Okay. Neat fact. In RN, there is a natural correspondence between points and vectors, and that's weird. It is very surprising at first glance, because after all, points have locations. Vectors don't. Vectors are directions and magnitudes. Vectors, being directions and magnitudes, don't have location, but points do. Right? Points don't have directions and magnitudes, but vectors do. So they have sort of complementary features, and it doesn't seem clear why there would be any correspondence between them. Anyway, it turns out that there's a very natural way to do this. Here's the choice. If you give me a point, right, then the naturally corresponding vector that I want to associate is formed in the following way. The vector is formed by starting at the origin. Now, let me confess, that's an arbitrary choice, but it's standard, conventional choice that we're going to use here. Start at the origin. Let that be the tail of an arrow whose head is at the given point. That then defines a vector by way of direction and length. And of course, then I can represent that same vector with different arrows. Right. So anyway, this is the correspondence. Notice that if you give me a point, there is exactly one corresponding vector. And if you give me a vector, there is exactly one corresponding point. And let me just to emphasize, if you say, hey, what point corresponds to that vector? Well, now let's take a moment and recognize that thing that I have circled in red, it's not technically a vector, that's an arrow. The vector that I'm talking about there is just the direction and magnitude described by that arrow that I've drawn. And the natural correspondence requires that we talk about that same vector with its tail at the origin. And that then describes this corresponding point. Okay, so every point there's a vector. For every vector there's a point. Okay. With that in mind, we tend to I say we, lots of people, myself included, when you're doing business in RN, we kind of blur the distinction between points and vectors. I emphasize they are not the same thing. They're clearly not, right? Points have locations. Vectors don't. Vectors have directions and magnitudes. Points don't. These are not the same thing. But if I use a point to describe a vector, come on, you know what vector I mean. And if I use a vector to describe a point, well, look, it's this correspondence. It's clear what point I mean. Right? And it turns out that blurring this distinction in notation is very, very convenient, and I'm going to do a lot of it. Anyway, so notations. This vector here, that vector, very often we're going to represent a vector by give it a name like V. Not very creative, right? V for vector. We put this little arrow hat on top of it as just a kind of a doff of the cap. Kind of a recognition. Hey, by the way, don't forget, that's a vector. That's not a number. This is not 6. Right? This is a completely different kind of object. This is a new critter. This is a vector, not a number. Okay. All right. A lot of textbooks use bold. I think that's a cheap trick. I feel like they're showing off because bold, while it looks great in a book, it's really hard to do with a pencil. Right? You got to sit there. It's super annoying, right? So I feel like books that are using bold are doing something to be viewed by students that can't possibly reproduce it in any reasonable way. So I'm highly opposed to the bold idea. I don't ever do bold, but you'll see it out there. So heads up. Keep in mind the point. Right? We have this old choice of how to represent points, namely as an ordered pair. That's long ago. Really, you can use those same coordinates then to talk about the corresponding vector. And a lot of books, ours included, will use triangular brackets to emphasize that they're talking specifically about the vector corresponding to the point with those coordinates, as opposed to the point with those coordinates. Right? And so the little triangular braces is a sort of a way to emphasize vector. I mean vector. No ambiguity. I like to point out that context always makes it clear, though. Right? If somebody says, hey, my velocity is, well, I mean, they're not going to be talking about a point. Right? My velocity is, well, they're about to use a vector. They're about to talk about a vector because, well, vectors are what describe velocities. Velocities have directions and magnitudes. Velocities don't have locations. If I say my velocity is New York, that doesn't make any sense. Right? So clearly I don't mean the point if I say my velocity is. Right? So I don't worry about this distinction myself. I am perfectly happy to use either to represent either, and then, again, the context should make it clear. Okay, so heads up for that. I mean, I'll be doing a lot. The book does not. The book is very careful to be sort of precise on that. And then, by the way, writing the vector's coordinates vertically, also you'd be surprised. It's very handy in a very large number of circumstances. One of which, a small one, we're going to see today. It's just an arbitrary choice, writing coordinates vertically, but I will be doing a lot of that as well. Okay. All right. Let me pause for a second. Take a breath. See if anybody has any questions. How are we doing? Yeah.
So the x1, x2, that's for the point or for the starting ending of the vector?
Yeah, well, so given a point, right, then I'm going to define a corresponding x1 and a corresponding x2 like this, and that defines these coordinates. But then if I subsequently want to talk about this vector, how would I describe this vector? Well, I could say, look, it's the vector that corresponds in the usual natural way with the point that has these coordinates x and y. Yeah. So always from the origin. That's when we talk about the natural correspondence between points and vectors, always from the origin. Yeah, absolutely. Yep.
And on the previous page, on the last 2 lines, it says that they're not the same thing, and in other spaces, there
vectors and also symmetrical coordinates?
Yes, and that's a little bit of a deeper conversation, and it's a great question. This is a fine example of a wonderful question that I'm not going to answer here because it's a long story, right? But if you're curious, come talk to me in office hours. There's a very reasonable answer there, but it wouldn't be appropriate here. Yeah. So thanks for that. It's a very good question. Okay. Alrighty. So let's talk about algebra of vectors. What can you do with them? Given a vector, how do you compute its magnitude? This is an easy little starter idea here. We use the length of the arrow to represent the magnitude of the vector. Lengths, of course, are distances. Distances, of course, are sides of a triangle. Pythagorean theorem. I hope you all remember this one, oldie. So easy answer. If you want to compute the magnitude of a vector, it's the square root of the sum of the squares of the coordinates. So, cool. By the way, a little quick notational aside. I like to use, as I have it written here, the double bars to say magnitude of a vector. Some books will use single bars instead of double bars. So heads up about that. A lot of people would complain that, what's bad about this notation is it looks like absolute values, and so we have ambiguity. Right? Maybe this means absolute value. But do keep in mind, vectors and scalars are different things. Right? So there's not technically an ambiguity there. Now then you might come back and say, what if it's a one-dimensional vector? Right? What if n equals 1? Then that vector is in fact just a single coordinate. It kind of is a number. So don't we have a confusion? Well, if you think about it, and it's a good exercise for everyone to think through on your own, if you do have a vector in R1, that therefore there's one coordinate you can kind of think of as a scalar, its magnitude is its absolute value. So it's not a confusion, it's actually a very natural choice. So anyway, like I say, a lot of books like to use the single bars. I still don't. It just makes me feel better inside to have the visual reminder that, hey, by the way, I'm thinking of this as being a magnitude of a vector. So anyway, it doesn't matter. Take your pick. You can use either. Either is absolutely fine. Okay. Here's an exercise. I'm going to leave this for y'all to work out on your own, but if you have a vector with 3 coordinates, then it's still square root of the sum of the squares of the coordinates to compute the magnitude. This becomes a geometry problem. This is no longer a triangle, so you can't just say Pythagorean theorem done. Right? However, even though it's not a triangle, it can be sort of modeled by 2 triangles, both of which are right triangles. Right? So I'm going to leave the details for y'all, but if you want to compute, the hypotenuse of that purple triangle, which namely is the magnitude that we're interested in, write down the Pythagorean equation as it pertains to both of these triangles. Play around as necessary, have fun, and the punchline will be this. So, good exercise for y'all to do on your own. Okay, so let's talk about how to add vectors. How do we add vectors? And you'll notice my choice of terminology here. I ask what should be the definition of a sum of 2 vectors. Seems like a weird way to phrase it. I want to point, there's a big point here, it's kind of a philosophical point, but we do not have a pre-existing definition of plus in this context. Now I know y'all feel like, come on, I remember that from elementary school, right? Come on, plus, it's our old friend. It's our most familiar operation. But the thing is, every use of plus that you've seen before vectors, you were adding numbers. Vectors are not numbers. They are a brand new kind of critter, right? And it is not just default automatically defined what it means to add 2 vectors any more than it is just default automatically defined to talk about what it means to add 2 cars. What is Toyota plus Chevrolet? That's not defined, right? So we're in a situation where we have we would like to define this notion. It seems like this might have potential to be useful. So we have to choose what we want that definition to be. Definitions do not come from on high, right? Definitions are not derived or found. Definitions are chosen. We get to decide what we want plus to mean for vectors. And I say we, I don't mean you individually. We don't all get to make our own choice, right? But the mathematical community had the opportunity at some point in the past to choose what to define plus to be. And so I want to talk about what the motivation for that choice is. I mean, I can write down the formula. It's in the book, read it, right? But I mean, the more interesting question is, why is that the formula? Well, let me remind you what vectors are. If we want to talk about the addition of vectors, maybe we better remind ourselves how we think about vectors. My favorite, I think, easiest way to segue into this is to recall that vectors, among other things, represent displacements. So if I'm going to talk about adding vectors, in effect, I'm talking about how should I add displacements, right? And so let's think that through. How should I add displacements? Well, here's a couple of displacements. There's a displacement. I'm going to draw it in standard position. Oh, sorry, terminology. Standard position means tail at the origin. So there's a displacement drawn in standard position. Here's another displacement drawn in standard position. What would feel physically like a natural, reasonable choice of what it should mean to add two displacements? I think it's I propose the following. I think is highly plausible. Well, how about I start at the origin and then do the one displacement, and then from wherever I end up, I do the next displacement. Follow the instructions and subsets. So let's displace by V. And then from there, let's displace by W. I think it's extremely reasonable and natural, emphasis on natural choice to make for what it ought to mean to add two displacements. And if that's what it's going to mean to add two displacements, then let that be our choice for how to add two vectors. Right? So the punchline is you take the, let's say the second vector, doesn't matter which one, put its tail on the head of the first vector, right? And then whatever, tail of the first to head of the new second, that is the sum of those two vectors. Okay. Now, that's a choice, but notice now we see this is not an arbitrary choice. This whole head to tail thing, I never understood this when I was in high school. I saw this definition in high school and I thought, okay, weird, whatever, I'll play, but I don't get it, right? But I think now this is extremely natural from the point of view of displacements. And you can make similar motivational arguments from the point of view of like velocities or forces and stuff like that. But okay. So with that in mind, if you try to write down a formula for this sum of two vectors, and if you look at the geometry of what's given, what do you know about these two given vectors? It's not hard to write down the little analytic geometry and go through and persuade yourself. That's what the formula for that new vector ends up being. Right? So this is our motivation, and then this is the resulting consequential formula for how to compute it. Okay. Now, let me dispel a myth. A lot of people, I think, really importantly misunderstand and think, oh, this is the definition of vector addition, because doesn't that seem like a reasonable choice because look how easy it is algebraically. That's lame, right? There's all sorts of things that we could write down that would be easy algebraically and would be horrible choices. I mean, here's what this is a silly thing. When I was a kid, I think I was young enough that this isn't embarrassing, okay? But I was memorizing my multiplication tables, and come on, that's hard. There's so much, there's so much to memorize. Seems like, how about 6 times 8? Why does it have to be whatever it is? Why can't we just make this 68? Wouldn't that be easy? Right? Algebraically, I challenge you to come up with an easier formula than this. Right? Easy. Useless. Right? So again, I was super young. Well, so the fact that something is algebraically easy is not a persuasive argument for why we should write a formula down that way. So the fact that it's algebraically easy is, silver lining. That's kind of cute and all, but that's not why. This is why. Does that make sense, everybody? Okay, how do we multiply a vector times a scalar? Well, we play the same game. How should we define a scalar times a vector? What should it mean to take a displacement, right, and do, c times that? And again, arbitrary choice, but I think it's geometrically satisfying to think that, well, c times a displacement means we'll just go that same direction c times as far. And so you draw that picture, and then it's really easy to motivate this formula, which again, lucky break, algebraically convenient. Check it out. You just multiply that scalar times all the coordinates. How nice, right? That's convenient, but that's not a good reason. The good reason is because it's geometrically natural. Okay. How do we subtract? I'm sorry, I got ahead of myself. Sorry. We have two operations. We have scalar times vector, right? And we have magnitude. So that gives us the opportunity to ask how do they relate to each other? What is the magnitude of c times a vector? And it turns out that it's the absolute value of c times the magnitude of the original vector. Algebraically, I think it's highly plausible. A lot of people mistakenly write that the magnitude of CV equals, and let me put a question mark here, c times the magnitude of v. Kind of rolls off the tongue a little bit more nicely like that, but it's false. It's not always true. In particular, it's not true if c is negative. Right? If c is negative, this will be a positive number, right? But this will be a negative number. Clearly not true. Now, so how do I know that there's an absolute value in here? Is it just something I throw in there to fix the problem that I saw? That's not a good argument either. Just because it fixes the problem I saw doesn't mean there aren't other problems. Okay? The reason that absolute value is in there is because you can write down formulas. You can take this expression here and you can explicitly write down square root of, let's see, it's going to be CA squared plus, let me do it like this, V1 squared plus CV2 squared plus, etc., CBN squared. And you can start rewriting that. And what you'll find in the process of rewriting that is you find yourself with square root of c squared on the outside of the original magnitude. And what is the square root of c squared? Again, common misconception. A lot of people think square roots undo squares. That's a gross oversimplification told to elementary school students. It's not true. This symbol here means the positive square root. Right? It doesn't mean whichever is the one you were looking at, or whichever you prefer, or something ambiguous like that. That means positive square root. And so the square root of c squared is the absolute value of c. It's not c. Okay, so anyway, heads up about that. Again, common misconception. The big news item I think for a lot of people is in what this symbol means. Again, that means positive square root, non-negative square root. Okay, yeah, right. Okay. So fill in the details. This would be good exercise as well. Oh, by the way, just a course mechanics observation. I'm going to do a lot of that in this course. I'm going to say, hey, this would be a good exercise for you all to fill in the blanks on. And I do that in situations where I think it's something that you should be able to do on your own, and there's value in actually working out ideas on your own. Right? And making that sort of, in some sense, a little personal discovery. And the class is really packed, and a lot of material we have to cover, and I have to be very, very picky and choosy about what I spend time talking about in class. And things that you can work out on your own very often don't make the cut. I'll also point out that little micro exercises like this of things I suggest that you work out on your own are things that I think are interesting and that you're capable of, which are two of the same requirements that I use when I'm coming up with test questions. And so it has happened kind of randomly, I'll say, on many occasions that things that I've made as suggested exercises in class happened to turn out to be exam questions. So there's another motivation for you to do those. So anyway, I think this would be a good practice problem. Fill in those blanks. Make sure you can do that. And by the way, also always, whenever I make these suggested exercises, if you get stuck, ask for help. Right? You don't have to, beat down that brick wall with your forehead. Right? So you're welcome to come to my office hours. You're welcome, of course, to go to the help room. Oh, let me also emphasize, y'all are welcome at the office hours of all of the instructors of Math 212 this term. Well, there's only 2 of them, but still, you can go to their office hours as well. So that, both of them will be very capable of giving you good help. Okay, so seek help if you need it. All right. Okay, how do you subtract 2 vectors? Subtraction is a combination of addition and scalar multiplication. We already have a definition of addition. We already have a definition of scalar multiplication. So subtraction is already defined for us, whether we like it or not. Good news, we do like it, but it is already defined for us. A different way to think about it, rather than sort of algebraically consequential of other things, is notice that this little triangle of arrows fits together, right? So what is v minus w? Well, v minus w, it kind of has to be the vector that you would add to w to get v. So, geometrically then, if you have a v and a w, this picture, head-to-head, you might call it, is a picture of v minus w. I think that's lovely. And very often that's how I tend to think about vector subtraction. Here's another point of view. Some people like this. I don't know. Some people like it. Some people don't. Let's go back over to here. Vector addition. You can think of vector addition. Adding w, the process of adding w is arguably the process of taking the head of v and scooching it over, leaving the tail the same. And likewise, you can think of subtracting w as the process of taking the tail of v and scooching it over and leaving the head of v the same. So, I don't know. It's another way to think about it. Your preference. Okay, some algebraic facts. I'm going to go through these quickly. I'm going to leave all of these pretty much as suggested exercises to prove these. The first thing I want to point out, though, is you may look at these formulas and think, yawn, I saw that in 5th grade. And I just again want to point out, no, you didn't. Right? We just defined vectors earlier today. All right? So you couldn't have seen this. If you saw this in 5th grade, I am super impressed with your elementary school. Right? So this is a brand new operation talking about combining brand new objects, namely vectors. So this is a brand new property of that operation, which cosmetically happens to look a lot like something we all saw in elementary school. Yeah, true. Okay. But it is brand new, so therefore it's not obvious, and therefore it is something that has to be demonstrated. How do we know that this is true? So the way that you're going to demonstrate these 5 properties, you don't have to do all 5, but I suggest you do a couple of them, is notice that in each case, both sides of the equation, I can write down in coordinates. Right, I do have a definition of the coordinates of v plus w. And I have a definition of the coordinates of w plus v. And you can write out these 2 sides of the equation then in coordinates. And what you will find then is that the coordinates of v plus w and the coordinates of w plus v are all the same. And therefore, these 2 as vectors have to be the same. So that's the big strategy. Break it down to coordinates is the sort of the streamlined way to say that. So nice exercise. I hope you'll give those a try. Again, maybe, if you do a couple of them, you see the pattern, you kind of notice, okay, I see how this works, and they're all going to work. Okay. By the way, heads up, a little word of warning. Not everything that cosmetically looks just like an old formula from elementary school is actually true. We're going to see some formulas, depending on how fast I go today. Later today, we're going to see a formula that looks like it. Come on, it looks just like a formula from elementary school. How could this not be true? It's not true. Right? So that's why you really do have to worry when you have new operations. You got to be the very first thing you should think is, oh gosh, I hope this behaves the way it sort of looks like it ought to behave, and be prepared for disappointment sometimes. And on a test, if you use a property that's not true, you will get wrong answers and very little sympathy. So you got to be real careful about that. Okay, a couple of little quibbly, little micro comments we have to make. I have to define something called a unit vector. It's just a vector of length 1, a vector whose magnitude is 1. A couple of easy examples. Notice 1, 0, 0. Compute the magnitude, it's 1. So this is something we call a unit vector. Here's a weirder example, but that vector in R3. Punch out the numbers. What are the odds? But it turns out that vector has magnitude 1. So also a unit vector. As a notational point, the book refers to this vector here as I hat. They use a IJK to represent 100, 010, and 001. Those are the vectors, of course, that point, all unit vectors pointing along the positive directions of the 3 axes in R3. Right? So I, J, K are the choices. And that's fine. The hat is a little visual recognition, that, by the way, this is a unit vector. I'm pretty happy to assume that my listener remembers that and just write I vector. Right? I don't think there's anything wrong with that. If you just want to write I vector, it's perfectly fine. I can't imagine anyone caring. I'll also point out that it's also perfectly acceptable to call that E1. And let me just emphasize. So E1 is 1, 0, 0. E2, likewise, is 0, 1, 0. This is all in R3. And E3 is 0, 0, 1. So notice that in all cases, the subscript, oh gosh, what did I just do? I just clicked the wrong color. The subscript tells you where the 1 is. Which coordinate that single 1 is sitting in. So, who cares? What's the problem? Why not just stick with IJK? Well, let me remind you, we will not exclusively be doing business in R3. And if you're doing business in R17, okay, well, what are we going to call those vectors? I guess we could call them I, J, K, L, M, N, O, P, Q, R, S, T, U. You see it gets out of hand. Right? It gets weird. But if you're using this notation, the E subscript, then what do we call those 17 vectors? Well, E1, E2, E3, E4, E5, just use the subscripts all the way down to wherever. That's fine. So it's much more generalizable. So I tend to, my personal preference is I use these notations. I tend to not like those because I've made the transition, and I like not having to worry about whether my notation's going to be a problem for me. Right? So I like this, but you're welcome to use IJK if you're in R3 if you want. Okay. Right. Neat fact. Another little exercise I want you all to follow through and think about the details of. But if you have a non-zero vector, then here is a handy-dandy little formula for finding a unit vector pointing in the exact same direction as your vector. This is going to end up being really, really important. It's surprisingly commonly the case that we are going to need a unit vector pointing in exactly the same direction as a given vector. So having a handy-dandy formula that just automatically does it is super nice. So this may be the most important formula that we're seeing today. So I hope you'll make sure to memorize that formula. You notice, by the way, you just take the vector that you're given and divide it by its own magnitude. Super easy. Right? Since I'm only multiplying by a scalar, this is obviously going to point in the same direction as V. Is this a unit vector? Well, notice I can take the vector and I can compute its magnitude. And the magnitude, a couple of details to work out, but the magnitude is 1, and therefore, yes, this is a unit vector. Right, so those details I want you all to go through and think about on your own. Notice that we are taking advantage of a previous formula that I've multiplied a vector by a scalar. Its magnitude then gets multiplied by the absolute value of that scalar. So we've already established that works, so we can do that. Okay. Last little bit before we go on to the next section is a little bit of terminology. This term here, linear combination, I'm going to use that term fair amount in this class. I'm going to use it endlessly in Math 216 for those of you who take Math 216, or if you take any other linear algebra class. It's arguably the fundamental construction of the entire subject of linear algebra, is the linear combination. And here it is, a linear combination of a collection of vectors. If you have a collection of vectors, linear combination says you're going to scale and then add. So anything that you can make by scaling and adding a collection of vectors is called a linear combination of those vectors. And by the way, here's a cute example of this, at least a cute property of this construction. Notice that if you have the vector ABC, then it is a linear combination of E1, E2, and E3. And furthermore, the coordinates of the vector are the coefficients in that linear combination. So that's neato. Right? This is a special property of these vectors here. These vectors E1, E2, E3, or if you prefer IJK, those vectors are the unique vectors that have this feature where the coordinates are the coefficients in a linear combination. By the way, this would be another good one to crank out. Right? Persuade yourself that this is true. Right? Write out the algebra. Crank out this linear combination and confirm that indeed you do get ABC. Persuade yourself that works. Okay, not hard. Okay, moving along. I'm going to talk about how to multiply vectors. Again, philosophically. I mean, this is not handed down from on high. We're not going to derive an answer here. We get to choose. Mathematical community got to choose how to multiply vectors. And what the mathematical community noticed at some point is that there are actually two good answers to this question. There's kind of there's two operations that we can write down that really seem like actually pretty good choices of how we really ought to multiply vectors. So in recognition of that, we are not going to talk about products of two vectors. We're going to talk about very specific kinds of products. Today we're going to talk specifically about the dot product. Please do not call this the product of two vectors. I don't know what you mean. There's two products. We'll talk about the other one Monday. But the product is ambiguous. There's a dot product that we'll talk about today, and there's a completely different kind of product that we'll talk about later. Here's the dot product. We call it the dot product in relation to the notation that we use. Notice that I put a little dot in between the two vectors. Very critically, it has to be a dot. This is not optional. You can't put a little times, little cross kind of thing. That's not okay. It's got to be a dot. And the dot product of two vectors is defined by this weirdo little formula right there, and it seems very much like I pulled that out of a hat. Right? I mean, why would you? I mean, you can almost kind of see that you would multiply corresponding coordinates. And that wouldn't raise anyone's eyebrow. But then why would you add the products of corresponding coordinates? What's up with the adding? Seems very strange. Yeah, it is very strange. By the way, here's another super weird thing. Notice that if you take a vector and another vector, their product is not a vector. Right? This dot product that I've just defined there, this dot product of a vector and another vector is a number. So that's weird and counterintuitive, right? When you multiply numbers, you get numbers. When you add numbers, you get numbers. When you subtract numbers, you get numbers. You add matrices, you get matrices, right? Every example that you may have ever seen before, you get the same kind of critter out that you put in, and not so with dot products. So I'm just saying it's weird, and heads up and keep that in mind. Okay, now nevertheless, I've written down a formula, and here's some boring algebraic properties. Yawn. Didn't I see those in elementary school? Isn't this old news? Why do we have to deal with the I remind you, these are brand new. You've never seen these before, because we've just defined that operation, right? Let me also remind you, you can't trust the idea that, oh, come on, it was even boring in elementary school. All those, they all look like they totally ought to be true. Come on, if it looks like it ought to be true, doesn't it kind of have to be true, right? And no. And let me show you. I referred to this previously. Let me end on this. Here's something that feels like it ought to be true, but isn't. Doesn't it feel like V dot W times U? Doesn't that feel like it ought to be equal to U dot V times W? I mean, isn't that like the associative property of multiplication or something? I mean, come on. What, isn't this obvious? It's obvious by syntactical beauty. Right? It lays out on the page so nicely. But this is crazy false. Not even close to true. Not even close. Right? So I emphasize, just because it looks like it ought to be true, just because it looks natural, doesn't mean it's true. So you should, as a result of this little weirdness, you should be highly suspicious. Wait a minute. What about these? Are these actually true? Check them. Right? Take a few minutes. Again, all you have to do is just multiply out both sides and observe. Yeah, sure enough, these are in fact exactly the same thing. But you've got to actually write that down. Okay. All right. And that's a good stopping place for today. See y'all on Monday. Have a great weekend. Have a good one.